product here, indexed by t, beta t. Well, this is not going to go on forever. The integer is finite. So you're going to reach a point where the betas are going to be prime. And that gives you your tree. All right? So now we've convinced ourselves of two things. Integers are trees, and what I was doing here, grafting, really is integer multiplication. Okay, so grafting, you should think about it as integer multiplication, and raising is just doing the exponent. Okay, so now we want to say that you actually get insight into number theory by actually doing this thing. And I seem to be doing okay on time. All right, so what kind of problems could you gain insight on by doing this? I claim that if you revisit the so-called Eratosthenes sieve, you get some insight. And here's how you can retake the Eratosthenes sieve from the combinatorial lens. So suppose you can get all the integers, you know all the primes that are less than n. So assume your label set L contains all the primes less than some integer, let's call it q. So q could be prime or not. So less or equal, let's put here, less or equal to q. What I want is to produce all the primes. So the problem we want to solve is produce all the primes in the range q, so all the primes are bounded by q below and 2q above. So you have some integer, let's say I have the integer 10, and I want to produce all the primes that are between 10 and 20, okay? How can I use the algorithm to actually do that? So we use algorithm 1, the algorithm described, to produce trees of height. So you produce all the trees of height log star of 2q. So why log star of 2q? Because the highest power of 2 is the smallest prime. The highest tower of 2 is the smallest integer that you can get that is in this range. So this gives you a bound on the height. All right, so you produce all these trees. Now, a lot of them are not going to be in this range. Do we agree? So let's actually look at a specific example to see what the algorithm does. So let's say n was 10. What is this here? Let's say n was 10.
Sorry, Edinah.
Yes?
Do you want to say what is log star? What is
log star, okay. Log star is the number of logs you have to apply to a number. So log star is equivalent, so log star of n is the number, so it's log, the number of times, so the number of times, until this thing is less than 1. Okay, so I like to think of this as log star base 2. So essentially you're doing log until you get a number that's smaller than 1. And it essentially counts how big this tower is. So 2 to the power 2 to the power 2 to the power 2. Log star of 2 is going to give me 1, 2, 3, 4, 5. So log star of this is going to be 5. Is it clear? So I'm saying that I can bound the height of the towers that are the trees that I'm going to be looking at. And because 2 is the smallest prime, 2 gives me an estimate. So I don't have to produce infinitely many trees on the labels that I'm assigned. So that's part 1. Second part was illustrating concretely what the algorithm does. So I produce these trees, and I throw away numbers that are smaller than q, and I throw away numbers that are bigger than 2q. So you're going to produce some large numbers, you throw them out, and you only keep the good ones. So you're going to keep 10. 10 is 2 times 5. Oops. Okay. You're not going going to produce 11. 11 is not in your set. You can't produce 11. But you can produce 12. And what is 12? This is 2 to the power 2 times 3. You're going to produce, you can't produce 13. 13 is not in your set. But you're going to produce 14, which is 2 times 7. You're going to produce 16. 16 is actually a very nice tower. 2, 2, right? Root. Right? 4 power 2. You get 16. 17 you can't produce, sorry. 18 you can produce, right? So 18 is 18 is 2 times 9, right? So this is 3 squared.
So Edinah,
Yes.
the 2, 2, 2 is 8, right?
So 2, 2, 2. No, it's not 8 because 2 to the power 2 to
My
the
bad,
power
my
2.
bad.
So this is 4.
Okay.
Yes, you're back. -1. Okay, sorry. Just joking. So this was 18, I believe. 19 we can't get, sorry. But we definitely can get 20, which is 2 to the power 2 times 5 roots. Okay. Sorry? Yes, we have 15. Thank you. Thank you. So 15 would be right here. We can get 15. Thank you very much. So let me put 15 here, which is 3 times 5. Okay. Is there another number I'm missing? I think we have them all. So the idea for the algorithm is to produce all these trees, evaluate the ones that are greater than 2q, you throw them out. The ones that are smaller than q, you throw them out. You only keep these guys. And now we're ready to detect all the primes that are in between q and 2q. So by the way, why do we know there exist primes between q and 2q? So the hard work has been done for us. Edinah and others proved that for any integer, there's always a prime between q and 2q. We just did not have a construction to uncover them all at once besides sifting the Aristotelian or variants of it. Okay? So now we're actually going to produce these guys. And I can, once you have sorted these guys out, every time there's a difference of 2 between consecutive elements of your tree, there's a prime missing. Okay? So the claim is, so this doesn't only work for this example. We're going to prove it in a second. Every time that, so this guy is 10, and this guy here is 12. The difference between 10 and 12 is more than 1, is 2. We know we're missing a prime between those two. So we flag here, there must be a prime here. Okay. All right, so then we come here. This guy is 12. This guy here is 14. There's difference of 2, so there must be a prime here. And here comes a beautiful example. So 14, 15, difference is only 1. There's nothing, no prime in there. 15 and 16, difference is only 1. There's no prime. 16 and 18. Oh, there's a prime missing. We flag. There must be a prime here. And this is 16 and, oh, sorry. So
18 and 20.
So 18 and 20, there's a prime missing. Okay. All right, so now this is an example. This is by no means a proof by example. Let's actually prove that this construction would always work. So it rests on the assumption that we indeed can generate all the composites that are using the primes in our list between q and 2q. So that you have to give me if you agree with the first part of the talk. Okay. Now, granted that you give me this, the claim is no composite can appear between q and 2q that contains primes that are greater than q. Right? What is the biggest composite you can get in this range? Well, take the smallest number prime and multiply it by the next prime, p. Let's say that the next prime was L. 2 times L is greater than 2q. So the smallest composite you can create that uses a prime that is not in our list, in the label set, turns out to be outside our set. So we don't have to worry about composites that contain primes greater than q. So the only thing that can occur in this set q and 2q are either primes or composites that were built using the primes that are less than n. So this means that the Aristoteles sieve only needs as input primes less than n. So instead of giving it all the integers, you just give it prime less than n, build trees of integers, and sieve out always, detect where the primes are. So you have to encode these primes as new labels, and you would increasingly detect primes between n and 2n. Okay, so yes?
Is there any sort of bound on how many, crap trees you will generate with this?
So yeah, this is a very good question. If you just do combinatorics, this is horrible. You create a lot of trees, unfortunately, and here's how you get a sense of how many trees you get. So G1, we already said, has size 2 to the n. Oh, I'm almost done. So it's almost time. All right. So this was a question. So here it is. We said that G1, the size of G1, is 2 to the n. Remember? Okay. And by grafting these trees, really you're doing something analogous to expanding expressions. So the G2 is going to have size 1 plus 2 to the n, the whole thing to the n. Okay, because there are n different primes. So you have 1 plus 2 to the n, these are the G1s. You have the roots that allows everybody to repeat, and this goes to the n. So G3, unfortunately, is going to be 1 plus 2 to the n, the whole thing to the n, 1 plus the whole thing to the n. So you see this grows horribly fast. In other words, combinatorics alone is no good. At some point you're going to need number theory to actually chop off these trees. So I leave you with the question. This is that's the time to go. So the question is the following. The question, now we're ready to include some number theoretical question. We pointed out that really these trees are rooted subtree of a complete n-ary tree. So let's draw this. We start at the root. Let's just use 3 labels. Okay, so 2 is allowed, 3 is allowed, 5 is allowed. Everybody has a maximum number of children. 2, 3, 5. 2, 3, 5. 2, 3, 5. And really, the whole lesson of this talk was to say that all integers, somehow, there's a set of integers that are rooted subtree of this big tree. If you just wanted to, just chop off the tree here. Let's say you wanted 6, just chop off the tree here. So the real question here is, this regular tree does not really reflect the structure of integers. It turns out that the tree is not regular. So let's see what I mean by that, and we're done. So we said that if you wanted 2, this is 2, this is 3, 4. This tree contains 2, 3, 4. If you want 5, you have to add 5. If you want 6, 6 is already in. 7, you have to add. 8 is here. 9 is here. 10 is already in. 11 is not in. So let me put 11. 12, I believe 12 is in. Okay, the point is, the tree that you end up creating is really unbalanced. There's one side that's favored much more than the others. So somehow you have to chop up the regular tree in such a way that you have a tree that contains consecutive integers, the smallest possible tree. So this argument needs more than combinatorics, it actually needs number theory, and this is the direction in which we're going after this step. Thank you.
What time is it? Is it time for questions?
It's 44, so...
Oh, so time for a few questions.
So I can get a few questions.
Yeah, this is a little bit reminiscent of Gödel numbering.
Yes, and that's actually a deep insight. So the idea here is that the Gödel numbering trick is not a trick. I personally believe it's a theory. So there is one idea of counting things. That's combinatorics has propelled that idea. Counting is useful. But when you can actually say something about structurally how you map to integers, in those cases, you do a bit more than counting. You're actually mapping structures from one set to the other. So in other words, I can talk about group theory on trees. And I can map all the structure of integers onto trees, and being able to do that map, actually, I would argue, is doing something more than counting, is doing structural counting, and there might be some meat to that. So thanks to Dr. Z's experimental math class, I've never thought about this. Any other question?
Thank you very much. You are most welcome to join us for dinner in Edo at 6:45, 68 Eastern Avenue, New Brunswick. But please let me know right away whether you can make it.